Okay, hello everyone. My name is Hao Sun, and I'm currently a second year PhD at ETH Zurich. And this is a joint work with my supervisor, Professor Zhendong Su. And also, thank you very much for the EBBL Foundation for funding our work. And so let's now talk about our approach, lazy abstraction refinement with proof to improve the verifier. Okay, so one of the most attractive features in this subsystem is that we have internal verification. So the ultimate goal here, I think we have two ultimate goals here. Goal number one is that we want to always prove the property if it holds. That is, we want to accept all safe program. And the second goal is that we never prove the property if it does not hold. So that is, we want to reject all unsafe program. So in an ideal world that we can achieve a both solid and complete verifier. But the reality is that in computer science, we always have to face the decidability issue. And in program verification, validating any non-trivial program verification and a property is undecidable. And I believe in eBPF, before we supporting loop, the problem is decidable. And after we supporting loop, especially with, even though we know it's terminate, but we don't know the iteration number. So I believe the problem is still undecidable. But please prove me wrong. Give me some hope if you know how to prove this. So anyway, so in this work, we're going to not going to achieve a complete verifier because I believe it's undecidable. We're trying to push the boundary of the verifier's completeness. That is, we want to make more BPF programs to be accepted. So I will very brief summary to the verifier because I believe most people here are very familiar with verifier. So it's based on abstract interpretation, but it's not very similar to classic abstract interpretation because we don't have any join operation. And the widen happen also very infrequently. And we track program state using range, interval domain, and trace state domain, and we identify using identity tracking, and we also prune paths by comparing current state with known safe state, and we use fixed point computation to handle loops. So I will start by discuss some imprecision sources. So fundamental sources of some imprecisions, that is the limitation that we cannot solve by using a better implementation. So as I mentioned, we use interval at a trace state domain to handle ranges. So for interval domain, the addition and subtraction is pretty good. We can provide a very tight range. But if we encounter any underflow or overflow, then we lose every information. So overflow is unlikely to happen, but underflow can be easily happen. If we see the example here, if we try to subtract to a variable with same range, then the range is bounded in onside domain. So also for multiplication, it's similar, but we are more easily to reach overflow because now the computation is more complicated, and we lost all information if the range is cross side boundary. So that's for multiplication. And for all the bitwise and shift operation, the interval domain basically doesn't work. We rely on another abstract domain called TNUM, trace state domain, to obtain the bound in different situations. And we lose our information. If any operate in a shift is a variable range, then we lose our information. So trace state domain. So this domain is a bit more interesting. We treat each bit individually, and we categorize them in three types: known to 0, known to 1, and we don't know, uncertainty. That's the third state. So because we treat each bit individually, so we can track all the bitwise operation and shift operation very precisely. We just use the extended truth table here to do all the computation. But it's not good at arithmetic operation. For instance, for addition, it's conducted by bit-level computation with carries. So unknown bits can create unknown carries, and both can be propagated very quickly. So for the example shown here, we can see before computation, X does not have any unknown bits, and Y only have one. But after computation, the higher three bits are all unknown. And the subtraction is very similar because it's conducted by bit-level computation with borrows, and unknown bits in this case create unknown borrows, and both can be propagated very quickly. And the worst case is multiplication. So in this case, the computation is conducted by partial product, shift, and addition. And in each step, we could lose some information. And all those steps are conducted many times. So we can lose information very quickly. So that's some basic limitations of those two abstract domains. And more importantly, I think more interestingly, it's neither interval or t-num domain track any relationships because they treat each variable independently. All the relationship is lost during tracking information. For example here, so at first we know that R1 and R0, they store the same source of input value. So after this however, after this shift operation, the verifier's ID tracking is lost after this shift operation. So in the non-taken path, in the for through path from 7 to 8, we know R1 is smaller or equal to 4. But the verifier cannot infer any information about R0. However, we know since R1 shift by 1 is smaller than or equal to 4, then we can know R0 is smaller or equal to 9. But the verifier cannot infer this because it doesn't track those computation. And here is another example. And I will use this example to demonstrate our approach, so I will elaborate a little bit more. So this case is from a real test case here. So as we can see from this program, it simply tried to conduct two memory access, right? The first one tried to access the max memory, try to write some information to the map. And the second access, write some data to the rest of buffer. So the program is perfectly safe. But the verifier cannot accept this. I will explain this very soon. And we have to double the size of this buffer in order to make the verifier happy. Okay, so why can't go back? Okay, so this is a simplified version of this program. So first, we use R0 to represent the size of first access, which is between 0 and 15. And then we add this offset to the pointer, R1. And R4 represents the second access, and the size of second access, which is 15 minus R0. And since verifier doesn't track relationship, and it can only infer the range of R4 is between 0 to 15. So when we add this offset to R1, the offset is between 0 to 30. So we lost all information and the access is deemed too unsafe. So but we know here R0 is between 0 to 15 and R1 and R4 is 15 minus R0. So we know the range is definitely safe between 0 to 15. The verifier cannot track this information. And there are many other limitations, but I will skip for now. So we have some existing work to handle all those problems. So for the work from Harry, they first proved the optimality of addition and subtraction in current t-num implementation. So that is, we cannot do better. That's the best we can do. And they also propose a new implementation for multiplication operation for t-num. And there are also other abstract domains we can consider, such as octagonal and I have a name, polyhedral. Okay, so that's other domains may be more accurate than interval and trace state number, but they are too complexity to material, and the reason about them is not easy. So we also have other work to improve the EPL verifier directly. For instance, the patch set from Android, we have better algorithm to derive information across different domains. And we also now support to track this information in jump history. And Alex also adds support to track constant data between links register. But so we should ask a question: can we solve the imprecision issue once for all, or maybe for many cases, not for specific use cases? So this is our proposal. We use a proof-based approach to improve this. So when the verifier rejects the program, what it really means is two possibilities. First, there are some feasible state in our approximation. That is, the state can be reached during execution, and they are unsafe. The second possibility is that there are some infeasible state in our approximation, and they are unsafe. So because the verifier cannot differentiate those two situations very easily, so we have to be conservative and reject the program and believe the state is a feasible, unsafe state, while the user space believes the opposite. So how do we handle this? Let's do something different. Let's not view where we cannot continue. Let's not reject the user immediately. Let's try to view this as a signal that it's time for us to refine our range. Because this is always the case, this is a very good point to refine the range. So this is the first laziness aspect of our approach. Second, when we try to refine the approximation, we can do very small work. We just refine it to just enough to continue. So here is the workflow I will explain very soon. So basically, we let the verifier continue as long as it can. And when it cannot continue, we symbolically follow current path and produce a refinement condition and give it to user space. If the user space can prove this condition, and then they give us a proof, a machine checkable proof. If we can check this proof and this proof is valid, we can then apply this refinement, and we can have a better and narrowed range to continue the rest of verification. So this is the key idea of our work. We try to produce a refinement condition and prove it in user space, and finally check and accept the refinement. So let's go to dive into the detail. So here we want to refine this range, which is too wide because it contains some unsafe state. We try to refine this range to safe range, but we of course we cannot do this unconditionally, otherwise it's unsafe, right? So the condition here is that the state, all possible value contained of current target register must be contained in this range. If we know this hold, then we can refine the over approximated range to this safe range, right? So this is the what we call refinement condition, but that's just a very bad word. The key point here is just the all possible value must be contained in a safe bound. So how do we know this? The verifier now approximate all possible value of a register by using interval and trace data, but obviously they are not precise enough. So now we have to use some more accurate, more precise domain to represent this information. So we use symbolic domain. That is, we make every input as a symbolic value, which can represent arbitrary 64-bit value. And then, for each computation, we just represent the equivalent computation symbolically, and record each path condition for conditional jump. So for the example here, we can see, assume R0 is binded to a symbolic value here. It could be arbitrary 64-bit value, and R1 is 1. So for this computation, we just use the equivalent expression here, but we replace each variable with its expression. Here we replace R0 to symbol 0, replace R1 to 1, and then we know R2 equals to this value. Actually, it's binded to this value, not equals to. And then for each branch condition, we remember if in the path taken, branch taken path, we remember this information. And compared to interval and the trace data domain, this symbolic domain can capture the exact semantic, capture all the computation conducted on the register. So that's the most precise representation of this register. But it's really hard to reason, right? Because all we know is just expression. We don't have any read information. We don't have anything else. So it's really hard to reason, but easy to collect. So we use this example here. So first, R0 is binded to a symbol value. And then for pointer, we track offset individually. And here, it's a constant offset. So after the first operation, we update the symbolic expression, use this add operation. And when we add this offset to R1, the offset is updated accordingly. So you see all the computation here is precisely captured. At R4, again, it's 15 minus this symbolic expression. And finally, when we add again to R1, we get a new expression here. And the verifier only have a range here, but we have the exact expression representing all possible value of this offset. So here is the expression we need, represent all possible value of this offset. So now, what we need to do is to reason about this expression. We want to know if this expression is between our safe bound. If it's between our safe bound, then we know the range, the verifier's range is too wide. We can safely narrow it. If it's not, if it does not hold, then we cannot do anything. So the goal here is to refine this condition. We want to prove this condition. We want to know if all the value represented by this expression is within the range between this safe bound, which is minus 16 and 0. We want to reason about this. Because if we know it, if we know this condition hold, then we know the verifier's outbound condition unhold, does not hold. Then we can refine the range accordingly. We can set the maximum value to 15 safely. So how do we reason about this? How do we reason this symbolic expression? Obviously, it's not easy, right? So we don't do this in kernel space. We produce this condition. We give the symbolic expression directly to user space. We ask them to prove. And if they can prove, they produce a proof for us. This is a machine checkable proof, and we just validate it in kernel space. If we know this proof exactly proves our condition, then we can accept it. We can continue our verification. So the whole point is proof here. So what is a proof? A proof essentially contains a sequence of steps, and each step is a very small and simple proof rule, as shown example here. So perhaps the most popular one is modus ponens. That is, we know A imply B, and A hold, then we know B hold. And transitivity, it's A equals to B, B equals to C, then we know A equals to C. So that's two basic rules. And the most important one is the resolution rule. The one I show here, basically we can prove everything with this resolution rule. That is, if we know A or L hold, and B or negation of L hold, then we can infer A or B must hold, right? Because L and negation of L, they conflict each other. So that's the basic rule. And a proof essentially contains a sequence of steps. And finally, it proves a goal. So here I show the common pattern of a valid proof. So if we want to prove phi of x hold, this formula, this condition hold, then we prove by contradiction. We first assume the negation of it hold. Then we apply a sequence of proof rule, and finally we can reduce this expression to false. Then we know negation of phi of x does not hold. Hence, phi of x hold. So that's the basic idea. So here is a concrete example. So for the previous example I showed, we want to prove this refinement condition hold. We want to show offset is bigger or equal to 16, smaller than 0. Let's just prove the left part here. So offset is equal to this expression. That's the premise of our proof. And we want to prove offset bigger or equal to 16. That's the left side of this expression. So how do we prove that? Let's assume the negation of it hold. That is, we assume offset is smaller than minus 16. And then we can perform a rewrite. And we know this expression, minus 16 plus this expression plus 15 minus the same expression can be reduced to minus 16 plus 15. And then the result can be reduced to minus 1. And since we know offset equals to this expression, so by transitivity, we know offset equals to minus 1. And with reflexivity, we know minus 16 equals to minus 16. That must hold. And with another rule called COG, we can see offset smaller to minus 16 is equivalent to minus 1 smaller than minus 16. And then minus 16 smaller than minus 1 smaller than minus 16 is equivalent to false. And by transitivity, again, we know offset smaller than minus 16 is false. Therefore, the goal does not hold. So we prove the assumption does not hold. We prove the goal. So that's a very, very simple example of the proof. And this is just a manual example. It doesn't follow any syntax. You don't need to care about the syntax here. It's not any formal language. So of course, in user space, we don't do this manually. We can do this automatically with the help of SMT solvers. So for our condition, as I shown here, for this condition, we can convert it to SMT formula here. But that's a negation of but we can then ask a proof from SMT formula. It can automatically produce a machine checkable proof, as shown here. And this one contains 17 steps because it also needs to prove the right part of the our condition, not just the left part. But the proof is basically what I just shown here. It's very similar here. So every step is a very simple proof rule, and we can validate very easily. So what does this mean? What is complexity here? So we give refinement condition to user space. And to reason about this condition, this is essentially the problem of certifiability model theories problem, SMT problem. And all we need to use is quantifier-free bit vector. And this theory is reduced to Boolean certifiability. And the set problem is complete, but it's designable. That is, for every refinement condition we give to user space, theoretically, they can produce a proof for us. So that's the most interesting part. Although we have a guarantee, they should be able to produce a proof for us. It's just a it's a matter of time. But in practice, SMT solvers can solve most formula very efficiently. So not a big problem of load time. So what we need to do in kernel space is just we first generate the refinement condition, which is done by follow the path symbolically. This is a ON, right? The complexity is very low. It's just the linear time follow the path. And in user space, although the problem is hard, the solver is really efficient in most cases. So we can get a proof from user space. We don't really care about how user space achieve this. That's their problem. And finally, we just do a check. As you can imagine, all we need to do is just follow each rule one by one. And finally, we can know what is proved in this proof. And that we check with our refinement condition. If it proved our condition, then we can conduct the refinement. And the benefit here is that we can achieve the precision of symbolic execution. Because we use symbolic domain, every information is captured exactly. And it's reasoning in user space, so we don't need to suffer from the complexity of reasoning aid. So that's the cost and the benefit. So in summary, so our approach is basically like, if you cannot continue, we follow paths, and we collect symbolic representation of target register, and we produce a refinement condition. And then we prove it in user space, and we check the proof. If it's accepted, then we verify and we continue. Because the symbolic domain is the most accurate domain, so we can hopefully handle many cases once for all. So this is the approach here. So I will talk a little bit about our current implementation. So we call this implementation BPF certificate format, or BCF for short. Originally, we want to call it BPF proof format, BPF for short. So obviously we cannot do that. So we just call it BCF, BPF certificate format. So now the program load command is extended with several fields. So user now can provide a buffer here, provide a buffer to kernel, indicate that if you cannot continue verification, please give me a refinement condition in this buffer. And when the user receives this from the buffer, it can produce a proof and write the proof in this exact same buffer. And flag is indicate many other things. So in user space, like it works by, if you don't use it, it doesn't influence your workflow. If you want to use it, you just provide a buffer. And then after the verifier reject your program, you check the flag if proof is requested. If it's requested, you can read the buffer, get the condition, translate to whatever formula you want to translate, and finally copy your proof to your kernel space. And users will typically use CVC5, or CVC5 has better support for proof. So currently I use CVC5. I use it to translate the refinement condition to formula, and then convert the CVC5 proof to the internal format, to the kernel internal format, and load it into the kernel. And in the kernel, what we need to do is, after every check, if we cannot continue, we check if proof is required, the BCF tracking is requested, because we don't handle every error, right? Some error just doesn't make sense. So we say if it's requested. If so, we start to follow the kernel path, do the check again. This time it's just for symbolic state tracking. So you can see here, if the program can be accepted directly by the verifier, this workflow it will not be triggered, so it doesn't impact you if you can already be accepted. It's triggered only when you cannot continue, and this is requested. And as I mentioned, we need to follow the kernel path. We do this by matching the jump history. And in check ALU, we just record the computation. That's just the basic map BPF opcode to BCF opcode. That's very simple. We just capture everything. And in the most top level, we see if proof is provided. If it's provided, we will resume last check. We just go to verifier checker. We don't do all those basic check. We just skip everything, try to resume. But before we continue, we will have a check step, BCF check. If it's passed, we continue. Otherwise, we skip. This verification is done. So I will show a demo here. Okay. So here we have a user space program called BCF client. We first not use our mechanism, so the program will be rejected. This is the exact example I showed you the slides. So the program is rejected, and now we use BCF. The program is loaded. So let's see why it's loaded. Let's take a look at the history. So first, in user space, we receive the proof request, and this is the formula we just received, and this is our goal. We need to prove this hold, and then this is the proof generated by the solver. We have successfully obtained a solver proof here. The step is basically just the proof rule I mentioned before, and then we give this to kernel space, and we can see the conclusion here match the conclusion of the proof match our original refinement condition. And I also added a little bit of change to the program. We have another execution path which also contains unsafe. The verifier believe is unsafe, and it's requested a second time. So again, we have a condition, we have our proof, and we give it to kernel, and kernel accepted it. And here is the verifier's log. It continues as before, and when it cannot continue, let's try to refine the offset, refine the variable offset. And we received here, we received the proof here, and after check, we continue. And we can see here, the range, the offset of R1 is refined to 0 to 15. It's refined. That's why the next operation can pass the safety check. And in another execution path, we again cannot continue. And again, we refine it. And here we can see the range of R6 is between refined to 5 to 15. And this makes the next instruction pass the verification, so program can be loaded. So this is the demo here. And that's all from my presentation. Thank you for your attention.
Thanks for the presentation. It's like really do you have any numbers on like the impact on the runtime for the verification? Like how much?
The runtime, I don't have a number of this because this is just prototype. I don't have. It's really hard to measure. So we don't have many unacceptable program by the verifier, while can be accepted by us. We don't have all those data set, right? Rejected by the original verifier, but can be accepted by us. We don't have that data set yet, so we cannot measure this systematically. But I can give you a number. It's so for the cases I tried, solver can solve them very quickly. And each proof, the size of each proof is basically within 50 steps. 50 steps. So the overhead, I would say, is acceptable.
So if you want to get such like examples, maybe one way to do this is to take the PDF programs from like Cilium at Tetragon, and we have usually a bunch of assembly stuff in there. It's usually when we can't pass the verifier.
Okay.
So if you remove this, maybe we get that example.
Queue of questions forward.
So if you have a complex program, like how do you find those locations that need refinement? Because it's also like a search space, right? I mean,
yes.
How do you iterate? Like, do you iterate through that, or like?
So currently, the refinement location is decided by me. So, like, because we cannot refine every point, sometimes we are for arithmetic operation, for all of the ALU operation, we don't reject program, right? Only for memory access and from some helper function call, we will check the memory access. And in this point, we may reject program. And so I added check in those locations. So maybe you can add this kind of request in other error report location. You can expand it. So currently it's decided by me.
So on a practical level, you're basically inserting finer range analysis results, right?
Yes.
Have you considered or experimented with removing more of the range analysis in the kernel and relying on your external proof? Simplifying the kernel logic and relying on external proof?
You mean simplify the existing algorithm and offload the most to users? Yes, we can do that, but the code is already verified. The existing code is already correct. Why do we want to simplify it? So if we can already verify in kernel, why do we
so we don't need to maintain it.
Okay, that's a point, maybe. But the current code is verified. I believe it's correct.
It would be a good result if you could basically duplicate what the kernel does. If you can show that you produce the same results and you can still get results from that.
Okay, so this reminds me of if we try to offload everything to user spaces, that's basically proof carrying code, right? We need to prove everything in user space. Then in this case, proof size would be very huge. Proof would be very huge. That's why I only do this occasionally, right? Only if we cannot continue. So if we offload this to a user space, that means the kernel verifier is very imprecise. That means we will request this proof many times, so it's very slow. So we still use the existing one, not to offload everything.
Thank you.
Related to the previous question we heard, how do you determine the refinement condition? How do you know what's the minimal refinement condition needed to actually prove the program?
Yes.
Is it also there are some heuristics, or how do you do this?
No heuristic. It's just computed. Like for memory access, we know the safe baud in the verifier, right? We know currently allocated stack size. We know the baud, safe baud here. So the refinement condition is basically for the symbolic expression, it must be within this allocated stack size. So this is dynamically tracked. The size is dynamically tracked that we can generate the refinement condition based on this. And in the other case, maybe we need other information, but we have all the information already in the verifier. That's why the verifier can know if the program is safe or unsafe, right?
Right, yeah, thanks.
Thank you. So you say like let's let use space do this. That's easy. We don't have to think about it. But I tend to live on the user space side of things, specifically the loader. So you're basically now making it my job to do all of this,
Yes,
all of this work. So what my question? So I'm a little worried about the performance side of this, right? So you said that in the cases you encountered, most of the time it's easy to do the formal verification, like at load time. But have you considered how often this might happen? Or so my thinking is, can I pawn this off to the user or to the compiler somehow? Would there be a way to perhaps do, might we expect where the verifier would fail, so we can do the proof ahead of time before the loader? Because, for example, when we ship a product, when you ship a product, you include all of the code, and it's way better to do perhaps lengthy formal verification ahead of time instead of doing it at load time. Because if you have to, at load time, when I want to load my program, I want to do it as fast as possible.
Yeah, I have considered that possibility before. That is, so to prove something, we first need to have something to prove, right? We first need a refinement condition. That's generated by the verifier. If we don't have verified user space, we cannot have that condition. We cannot have all the information. So another possibility that we have a user space verifier that basically does everything as an internal verifier. And then in this case, we can produce a proof ahead of time because we will know when the verifier will reject the program. We can know this if we have a user space verifier. But this brings another issue that we need to maintain the user space verifier again. So I choose to do this on demand and have the only verifier in the kernel. And I have to say, we need to make some change to the loader program because we will have to receive the refinement condition from the kernel, and then we interact with the solver. I believe this is a one-time effort, and I have a prototype for this already.
So slight follow-up question. So currently you stop the verification and then we have to resume.
Yes.
Would it be possible to have some sort of checkpoint or save where we are between these invocations? Because if you're in the middle of like a 1 million, if you're really close to the complexity limit, it currently already takes the verifier quite a long time to do it.
Yeah, that's exactly what I'm doing. That I snapshotted the verifier state, and then I verify directly on the same verifier state, and then we continue. So it will continue at the same point, not redo everything again.
Yeah, thank you.
Kind of building on what you were saying, it'd be cool if you could, when you're building the program, verify it once with the kernel verifier, instead of having the user space one, figure out what proofs you need, and then ship the proofs with the program.
Yes.
So then later when you're in production, you already have the proofs,
Yes.
and you can load them ahead of time.
Yes, I think we can do that. Like maybe we first use the user mode Linux to run it, and then we already know. We still have the same verifier, right? We use user mode Linux and run it beforehand, and then we save the proof together with the binary in maybe some arbitrary section in the binary, and then loader program can load it again.
Yeah, I think you can do that even without user mode Linux, by just using the real verifier the first time.
Yes, we can do that.
Easy.
Have you also thought about how to make that trustable, like when you re-inject the verifier state and the proof and so on, that the kernel somehow can be sure that this does not come from a malicious source?
You mean, so we can only apply the refinement if proof is valid. We have a proof checker. So if proof is malformed, we will reject the proof. Right? So user cannot provide arbitrary.
The checkpoint is the kernel memory, so it cannot be mangled by.
All right.
Hi, I'm also wondering, can we do the similar thing for the JIT compiler? Because we already have some use-based JIT implementation which transform the eBPF instructions into LVMIM machine code. I can implement a lot of optimization passes on it. So can we do a similar thing like we do the code optimization pass and recognize if there exists any patterns in your space, then move it to kernel for verify, then we can apply it.
Yeah, can you imagine that? But that's, I think, a different problem. It's like
Yeah.
something called certified compilation, maybe. You compare your code and you have proof that the code, the
Yeah.
native code match your original code, and you have proof to show that. But that's
Much harder?
a different story. I think the proof side would be much harder,
Okay.
much bigger. Because
Okay.
now we need to prove every instruction. For every instruction, we would generate many conditions to prove. So that would be
Okay.
very huge. Yes.
Okay, thank you very much.
Just a naive question. What is the size of a typical SMT solver in user space?
Oh, that's big. Because, so I mentioned in the slides, we only need a codifier-free bit vector. We only need this theory. But the verifier, the SMT solver currently does not support. I optionally make the rest of solver, just separate the rest of solver, because we only need one theory. But currently in kernel compilation of the SMT solver must encode everything in the same binary. So it could be huge. With debug information, it's 500 to 600 megabyte. But if we remove debug information, I think it would be much smaller. But I haven't tried. I cannot give you a number here.
Thank you.
Thank you for excellent talk. We're running a bit behind, so if any more questions, yeah, please reach out to
Yes.
Howard in the hallway. Thank you.